Welcome to all. I hope you are enjoying my video lecture on the YouTube. I have uploaded many lectures on the various topics in chemistry, especially NMR spectroscopy, stereochemistry, and a small part of the physical chemistry. It's a colloid. And I have completed almost most of the topics in NMR spectroscopy. And in today's class, I introduce some advanced concepts in NMR spectroscopy that is applicable in the organic chemistry. Let us go into the learning outcomes of this lecture. Okay, so whatever may be the comment you are having, okay, about my video lecture, you can at any time you can comment in the comment box, and you can mail me or text me in the message box. What are the maybe the details about my email and the phone number that is available in my YouTube. Okay, so the learning outcome, we are going to cover the four topics. The first one is the chemically induced dynamic nuclear polarization. Okay, so that is called CIDNP, where the polarization, that's the magnetization, is passed over during the chemical reaction. Are you follow my point? Say here, whatever we have seen in the coupling, the magnetic information passes through by the bond, sigma bond. But and in the NOE, the nuclear polarization that passes through the space. But here it's a chemically induced dynamic nuclear polarization. The polarization passed to the nucleus through the electrons, that is free radicals, during the chemical reaction. And second one is the restricted rotation. Okay, so one can find out using the NMR whether the molecule has a double bond character. A single bond molecule, they have the double bond character. So at room temperature, you know that the carbon single bond undergoes a fast rotation, very fast rotation, and one cannot differentiate between single bond and the double bond. But here by using the NMR spectroscopy, one can find out the double bond character of a single bond molecule. And the third one is spin-tickling. It is another mode of spin decoupling. Spin decoupling uses high irradiation radio waves, but here it uses very low intense radio irradiation. Okay, and finally the application of NMR spectroscopy in the medicinal field, especially in the diagnostic. It is a wonderful diagnostic tool in diagnosing the disease, which is called MRI. So let us go into the first one, that is a chemically induced dynamic nuclear polarization. Okay, so this is nothing but a CIDNP, already I told. Okay, and it is a technique used in nuclear magnetic resonance spectroscopy. The basic idea is to enhance a nuclear polarization of a specific nucleus by transferring polarization by electrons. Okay, the molecule during the reaction, if a free radical is formed, that free radical transfer its magnetic information to the nucleus. Okay, we call the polarization of a nuclear polarization of a specific nucleus by transferring polarization from electrons. This can provide additional information about the molecular structure and the dynamics. Dynamics means about the chemical kinetics. That is a reaction mechanism. So, for example, when we take the thermolysis of dipropyl peroxide, carried out in an NMR tube. Okay, the reaction is carried out in the NMR tube itself. Okay, in the thiophenol. Okay, in the thiophenol, first the ethyl radicals are produced. From the thiophenol, the ethyl radicals are produced. Then this then reacts with thiophenol to form the thiophenatone. So I have given the mechanism. So propionyl peroxide thermolysis. So on the action of heat, it forms a peroxide radical, the acetyl radical, and it gives a ethyl free radical. This ethyl free radical reacts with the thiophenol to form a thiophenatone. So here it involves a ethyl free radical that is easily found out by the technique CIDNP technique. Okay, let us see how one can find out the presence of free radicals during the reaction. That is whether the reaction mechanism follows a normal molecules or the free radical molecules, that one can easily find out by the this technique. Okay, so the NMR of the thiophenol, it is given. Okay, so we have the normal spectrum which is given. I have given the only for the ethyl fraction, that is the methylene CH2 protons, that gives a quartet because of the presence of the methyl, that is a 3 plus 1 4 quartet, and the methyl proton that forms that triplet. Okay, but if we go for the CIDNP technique, so already we have noticed that the free radical is formed. We have the two types of spectrum. One is up, that is called the emission. Okay, and that is a simulated absorption peak. So the simulated absorption peak A, and the down peak we call it is a simulated emission peak E. The upper peak, it is called simulated absorption peak A, and the below peak under the x-axis we call simulated emission peak E. Okay, that is the peak obtained when we use the CIDNP technique. Okay, so normal spectrum we will have the normal NMR things. So during the above chemical reaction, the nuclear spins in the product are undergoing dynamic polarization due to the formation of free radical intermediate. So already I told this technique is very useful to find out the presence of the free radical. This is a very good example of the CIDNP. So the next, the salient features of CIDNP is the observation of CIDNP in the NMR spectrum suggests the involvement of the free radical mechanisms. And here we have the free radicals both exist in the mixture of singlet state and the triplet state. Okay, so we have one interpretation that is in the mixture. If the singlet state's predominance, then the simulated absorption peak is more prominent, it is observed. If the triplet state predominance, then simulated emission peak is observed, which is more predominant. Okay, so the next topic is the restricted rotation. So if we take the carbon-carbon single bond molecule, we have the free rotation about the carbon single bond. But if we go for the carbon-carbon double bond, this is one. Okay, this is the one. We don't have the carbon-carbon single bond or double bond rotation. It is a restricted rotation. So if a molecule that is originally has the single bond character, and because of the resonance, if it attains a double bond character, that can be easily observed in the NMR spectrum, find out by in the NMR spectrum. So the conformational isomers, this is the one which is arises due to the carbon-carbon single bond rotation. At room temperature, it undergoes a fast rotation. So the NMR could not understand or find out the this one, the find out the carbon-carbon, find out the difference between the one conformer with the other conformer. But at very low temperature, the rotation rate is very slow. The NMR can differentiate between the one conformer from the other conformer. Okay, so the restricted rotation in a molecule arises due to the restricted rotation across carbon-carbon double bond forming as a result of resonance. So I will see the structure also, so that one can distinguish cis and the trans isomer. Cis and the trans isomer. So this is a cis, and this is a trans isomer. Okay, and if a molecule originally contains single bond, as already told, and because of resonance, if it attains a double bond character, this phenomenon is called restricted rotation. For example, consider the molecule NN dimethyl formamide. At temperature, the molecule undergoes resonance as this one, the lone pair of on the nitrogen, okay, that undergo resonance, making the carbon double bond O as a pi bond to delocalize. Okay, that gives a double bond character. So I have the structure 1, which has a single bond character, and because of the resonance, the structure 2 is formed, which has a double bond character. Here, if you take the structure 1, okay, at room temperature, as we expect, only 2 signals from the molecule 1. That is one doublet equal to 6 hydrogen. That is because of the presence of the 6 hydrogen of 2 methyl groups. Because of a rotation, single bond rotation, they are in the same chemical environment. We can say they are chemically and magnetically equivalent. Okay, they have the same chemical shift and couples with the proton B at the same magnitude. Okay, and one substrate okay. But actually 2 signals are observed for 2 methyl groups, okay, because of the restricted rotation. So we have the HC here, this HC, okay, this let us see this oxygen, the HC. Here we are having the 2 methyl groups. Here, because of the restricted rotation, this methyl group cannot come to here, and this cannot come here. This cannot come here. Okay, and because of that, we can call this CH3 proton as a and CH3 proton as a B. Okay, and we have the separate signal of A proton and the A methyl proton and the B methyl proton, and for the HB, which is a trans methyl, this is a trans methyl. It appears at the 2.79 ppm at higher coupling constant, because it is trans. At 2.94 ppm at a lower coupling constant, because it's a cis methyl group. This is because the cis methyl groups, and this can be explained by the presence of the structure 2. That is, the molecule attain the double bond character because of resonance. At higher temperature, the molecule undergo rotation at a higher speed, so that it cannot undergo resonance, and the spectrum will be spectrum follows the structure 1. Let us go for the spin-tickling. Okay, so in the double resonance, double irradiation or double resonance detecting, you see, it is also a powerful tool where one can find out the coupling partners, and here we are using a high intense irradiation, and when we use this type of high irradiation for the complex molecule, some of the useful information is lost. For example, if you take the furfural, okay, we are having the 3 protons of 3 different chemical environment. So this gives a pattern of AMX spectrum, AMX pattern. Okay, that is let us take the HA proton. The HA protons couples with the M proton, forming a doublet. Okay, also, okay, this HA further splits into 2 to giving the couples with the with X giving the another doublet. Once again I repeat, HA protons couples with the HM forming a doublet, also couples with the also coupled with the HX also HA couples with the HX, so that HA further split into 2, giving a total of 4 lines. Similarly, we can explain for the HM, which gives 4 lines, and for the HX, which also gives 4 lines. So 4 lines as a total of 12 lines of equal intensity, that is given by the AMX spectrum. Okay, so if you this is a spectrum. Okay, we have the 12 lines, and I have given the coupling coupling information also. Okay, and if you want to find out the coupling partners by using the double irradiation technique, okay, most of the information is lost. So here it is let us see the double irradiation. Okay, so if we irradiate strongly the proton HA, will be the spectrum, we will get the spectrum like this. Okay, and we will get the A peaks is collapse, and the other 2 peaks that gives the doublet, that will not couple with the HA proton. Okay, but on the other hand, if you use a spin-tickling technique, that is a irradiation with a low intensity, only the first line is disturbed. Disturbed. We observed that the second part of the 2 lines, HX and HM signal, are undergoing further splitting. That is 11 lines 7 and 8 and 11 signals. Signals 7 and 8 and signals 11 and 12. Okay, this is a spectrum. Okay, so we are irradiating the line 1 of low intensity. Okay, so let us see the peak 7 and 8, peak 7 and 8, that is disturbed. 7 and 8 and 11 and 12, that is disturbed. So we can get the further information that this infers that line 5 and 6 and 7 and 8 are associated with a different orientation of HA respectively. Okay, one may be plus off and other may be minus off. One may be plus off and another may be minus off. Let us just view the pattern of the splitting pattern of 7 and 8. Okay, it is different from splitting pattern of 11 and 12. So we can say the 5 and 6 and 7 and 8 are associated with a different orientation of HA. That is, one may be plus off, another may be minus off. So the similar argument can be applied for the last 4 lines. That is 9, 10, 11 and 12. 9, 10, 11 and 12. Okay. So since spin-tickling changes the splitting pattern of lines 7 and 10, before that I have to explain. Similarly, 5 and 7 are having same orientation of HM, 5 and 7. Okay. In the middle, the 5 and 7 that has the same arises because of the same orientation of HM, and 6 and 8 are associated with the opposite orientation of HM. Or you follow my point? Okay. So the similar argument can be applied for the last 4 lines. That means the 9 and 11 arises because of the similar orientation. Okay, same orientation, and 11 and 12 9 and 11 and 10 and 12 arises because of the opposite orientation. Since the spin-tickling change the splitting pattern of the line 7 and 8 and 11 and 12, one can conclude that these lines are arised from the same orientation of HA. Or if you follow my point. So what is the conclusion? So the line 7 and 8 and 11 and 12, that is affected because of the if we irradiate the line 1 which belongs to the HA. Okay, so that we can say the 7 and 8 and the 11 and 12, okay, changes the splitted pattern. So one can conclude that these lines are arise from the same orientation of HA. Same orientation of HA. So the conclusion, the JAX and the JAM are of same sign compare of the JMX. So the coupling constant of AX and the coupling constant of AM are same sign compared to the coupling constant of JMX. Okay. The final one is the magnetic resonance imaging and the MRI. That is it is a wonderful tool. Okay, the NMR spectroscopy, apart from the other applications in any industry, any part, it has a wonderful application in medical field. That is MRI, astonishing tool in the diagnostic era. So what we are doing here, a typical magnetic resonance imaging instrument use superconducting magnet with a field strength on the order of 1 Tesla. The magnet is constructed with a very large inner cavity, very large. I will show the diagram. Very large inner cavity, so that the entire human body can fit inside. Okay, and the transmitter receiver coil known as surface coil is positioned nearer to the body, that is outside the instrument. Okay, outside the instrument. So this is the instrumentation. We have the electromagnet, and the radio frequency coil is just surrounded the body. We have the cavity inside. A person can go inside, or the person can be fitted to the cavity, and the radio frequency transmitter is attached, and the magnetic power is varied by the gradient power supply. And we have the by the operating system, by using the computer, one can vary the magnetic field or the radio frequency transmitter. Okay, so and whatever may be the signal that is obtained, that is received by the radio frequency receiver, and it is processed by the image processor, and a three-dimensional image is recorded. Three-dimensional image is recorded. Okay, so what is the theory involved here? So the theory involved here is the using of water molecule. In the body we have the large amount of water molecule. Okay, so in the most cases the proton nucleus is the one which is studied, since it is found in the water molecules that are present in and around living tissues. Okay, this is similar to CT scan. But what is the difference is, in the CT scan, X-rays are used, but here in this MRI, the radio waves are used. X-rays are harmful to the body, but radio waves are not harmful to the body. Okay, so proton nuclei of water molecule that are not bounded within the living cells have a relaxation time different from the nuclei of water molecules bound within the tissues. That's bound which are not bound within the tissues. Are you follow my point? So within the tissues, if the water molecule is there, that which has a different relaxation time than the water molecules that bound outside the tissue, Okay, outside the tissue. So the water molecules that appear is in a highly random order state have a relaxation time shorter than the water molecule that appear in a more random state. Okay, the random state means the molecules go the water molecule go random motion. There is a free space that has the relaxation time shorter than the water molecule that appear in a more random state. So the degree of ordering of water molecule within the tissues is greater. So within the tissues means we have only a smaller space where it is in the highly random state, and the relaxation time size is shorter. Okay, so the degree of ordering of water molecules within the tissues is greater than that of water molecules that are part of the fluid flowing within the body. So where the randomness is more and the relaxation time is the longer. Okay. Furthermore, the degree of ordering of water molecules may be different in different types of cells. Okay, the radiographer know all the things. Okay, radiographer all the things about the degree of hardness of the water molecules present in the different types of tissues. It may be different in the liver tissues or the lung tissues or in the brain tissues and so on. Okay, so one can differentiate between the radiographer can differentiate between the disease cells as compared with the normal tissues. So what we are going to do is a specific pulse sequence detect these differences in relaxation time for the protons of water molecules in the tissues being examined. Okay, so a specific pulse is which is going to detect the differential relaxation type of the protons of water molecules in the tissues being examined. So when the results are scanned or processed, the three-dimensional image is produced, which shows different densities of signals depending on the degree to which water molecules are in the ordered state. Okay. So here we are having the MRI spectrum of the normal, okay, normal brain. It is taken in the top view, where we have the brain, the brighter area and the darker area is there, and we have the eyes, which is it's a soft tissues, which shows us a brighter area, which is in the brighter area, and we have the bone area, the backbone, okay, which is water deficient tissue, and it is in the darker condition. This is a diagram of our MRI of our normal tissues, normal MRI. And if you take the lateral view, okay, lateral view, this is the one where in the left hand side we have a brighter area. Left hand side we have the brighter area, the affected area, where the no blood flow is there and only the water molecule is there, no blood flow, and it appears as a brighter area, and this is a condition for the condition of the infarct, that is the MRI of the patient affected from the stroke. I hope you can understand all the topics that we have covered today. So thank you for watching my video in the YouTube. I request you to subscribe my channel. I am going to put more videos on chemistry topic for all the competitive exams like a TRB, the NEET, the UPSC exams and so on. If you like these videos, you like that, and share the videos to your friends, and give comments so that I can improve my video lecture. Thank you very much.